Suppose u equals x square minus y square and v equals minus y by x square plus y square. We check whether u and v are harmonic functions. That is, we check whether u and v satisfy Laplace equation. We also check whether f of z constructed using u as real part and v as imaginary part happens to be an analytic function. Recall the general result. F of z is analytic always imply the real and imaginary part of f of z are harmonic functions. Or if f of z equals u plus iv, it always happens to be true that u and v are functions that satisfy Laplace equation. Consider this as the statement P implies Q. By mathematical logic, we have P implies Q does not always imply Q implies P. That is, if P implies Q, it need not be always true that Q implies P. Hence, we have if u and v are both harmonic functions, it need not always be true that f of z is analytic. That is, if u and v are harmonic functions and you construct a function f of z switching u as the real part and v as the imaginary part, it need not be true that f of z is analytic function. But whenever p implies q is true, we have negation q implies negation p. That is, if you are able to conclude that u and v are not harmonic functions, or if you happen to conclude that u and v does not satisfy Laplace equation, then you can conclude that f of z equals u plus iv is not analytic. That is, if you happen to analyze that u and v does not satisfy Laplace equation, then the function constructed using u as real part and v as imaginary part will surely be a non-analytic function. Here we have u equals x square minus y square. We evaluate dou u by dou x, which equals 2x here, dou u by dou y, which equals negative 2y. When we evaluate dou square u by dou x square, we get 2, and dou square u by dou y square is minus 2. So we have the Laplace equation dou square u by dou x square plus dou square u by dou y square equals 0, which happens to be true for the given function u. Hence we conclude that u is a harmonic function. Moving on to function v, we have dou v by dou x, which can be evaluated using quotient formula. We get dou v by dou x as 2xy divided by x square plus y square the whole square. We evaluate dou square v by dou x square again using quotient formula, which is applied on this function. We get the final answer and we notate it as equation 1. Now we evaluate dou v by dou y using quotient formula. We get an expression which again we partially differentiate with respect to y to obtain dou square v by dou y square, again depending on quotient formula. We give the equation for dou square v by dou y square as equation 2. When we add equation 1 and 2, we obtain dou square v by dou x square plus dou square v by dou y square also equals 0, from which we conclude that v is also a harmonic function. You can notice that ux equals 2x here and vy equals y square minus x square divided by x square plus y square the whole square. Hence we have ux not equals vy. Similarly, we can also notice that uy not equals minus vx. Hence both pair of CR equations are not satisfied here. So we hereby conclude that even if u and v happens to be harmonic functions, f of z constructed using u as real part and v as imaginary part does not satisfy CR equation, and hence f of z is not analytic.